Okay, let's begin. Okay, let's start. So in the last class, we started to look at pipeline ADCs. Again, the idea is, basic idea is to have a multi-step conversion, wherein the general principle is to try to cancel the quantization noise of the first ADC. And for that, we basically took the ADC output, converted it into an analog voltage, subtracted from the input, and then before we feed it to the next ADC, we amplify it so that the amplified signal spans the full range for the second ADC. We do this so that we can squeeze out the maximum performance from the second ADC, right? And the way we reconstruct the final outputs are the following. We take the first ADC output, add it to the second ADC output, divided by the gain we have in the previous stage. And if you choose this gain to be the maximum value, then even the addition becomes trivial. You just need to take the two ADC outputs, concatenate them, and say that is the final data, right? And this is the effective resolution you have. It is essentially the resolution of the last stage plus log to the base 2 the gain you have here. And we kind of generalize it for, can generalize it for n stages also. And when you do it for n stages, the way you reconstruct the output is as follows. First stage, V1, V2 by G1, V3 by the gain it sees before, so I can take a 3 step. So first one comes V2 divided by G1, V3 divided by G1, G2, and you keep doing this. And when you do this, the quantization noise from all the previous stages completely get cancelled. You only end up with the quantization noise of the last stage, and that gets divided by the entire gain you have from the start to the end. And again, the effective resolution is the resolution of the last ADC plus log to the base 2 times. And once again, here if you choose the gain to be the maximum gain in each stage, even this final addition operation becomes a simple concatenation where you take each ADC output, concatenate, and give it as the final output.
So the DAC doesn't have any like mathematical noise being added.
I am at a block level, no. Circuit level, yes. I mean, basically DAC is simply doing this. We have digital codes 1, 2, 3, 4. It is just translating it to voltages. That's all. So ideally, it will not. Unlike an ADC, where the moment you digitize it, you have a quantization noise. This process, in principle, has no error. Right? In principle, it is basically taking this and multiplying with the voltage. It's a linear process. Cool. And this what gave rise to the pipeline. Yeah, in the this entire business can be done in 2 ways. One is where you apply the first input, waited for it to get processed by all the stages, and then you give the second input. But if you do this, the second input will come only after 6th clock period. So effective speed seems to be dropped by a factor of 3. An efficient way is to do pipelining like this, wherein when the second ADC is processing second ADC is processing the first input, you don't let the first ADC sit idle, you take the second input and do it. Okay. So yeah, so now again we have come up with something new, we have given a nice name. So what is the next thing we do? We'll see what are the possible problems we can have here and what is the fix for this, right? And here we basically have only these 3 blocks, ADC, DAC, and this amplifier taking the difference. We'll see what is the issue with each of these. So for that, let me draw a 2-stage pipeline first. So let us say this is the first ADC. You basically have a DAC here. So let us say this is Y, this is ADC1, DAC1. And you basically amplify this and then give it to the second stage ADC. And if the ADC has a resolution of D1 bits, what will be the gain you use here, maximum gain? 2 power B1. And how do you reconstruct the final output? V1 plus V2 upon G. That's how you do, right? So let me take some numbers for simplicity. So let's say this is some 2 bits. So the gain is going to be 2 power 2. Fine. Again, I just want to highlight the point. In a pipeline, the effective resolution only depends on the last ADC and the gains you have here. That's all. And one important thing to notice, to try to keep the output of the amplifier within the range for the second ADC, because only then this will be able to faithfully digitize the signal here, right? So it is very crucial to keep the signal here within the range for the second ADC. Good. So now let's see what will happen if there is some issues in the first ADC, right? So what are the possible things that can go wrong in the ADC? Nonlinearity. Okay, what else? Okay, let's not worry about noise for now. It's not circuit level is as of now. Okay, let's say nonlinearity. Let us say you can have offset anything, but at the end of the day, I can always translate it like this. Ideally, you need to have a step curve like this. Basically, you have made some error in the transition voltage. Anything you have gain error, offset error, nonlinearity. At the end of the day, the fact is the comparator threshold voltage has shifted to the left or right by some amount. So let's see what will happen if that happens here. And for that, let me first sketch the characteristic of this 2-bit ADC. So again, this is something we have seen before. I will do it again. So let's say this is the input. I normalize it with respect to the reference voltage. This is the quantized output, again normalized with respect to the reference. Let's say these are the ranges minus Vref to plus Vref. Fine. So I'll quantize it into 4 levels. It's not something like this. Right? Cool. So now any input in this range of 0 to 1/2, what might be the value to which you quantize it to? I mean 0 to Vref, what will be a reasonable value we'll round it off to? Huh? Sorry? 1/4. So that's what we will do. So let's say this is quantized to, let us say 1/4. And from 1/2 to 1, what will you round it off to? 3/4. So let's say that is something here. Similarly, in the bottom side, I'll have the same thing. Let's say this is minus 1/4. And minus 3/4. This is basically the quantized output. And let me also draw the y equal to x line. Since it's very let's say something like this. Okay. So this is basically the input, and this is the quantized input. Let me also try to sketch the quantization noise. Quantization noise is the output minus input. So again, I'll try to draw it on the same scale. So again, this is y by Vref. This is the quantization noise, again scaled with this. So let me quickly mark the ranges. So let's say this is 1. Cool. So now I'm going to take the difference between quantized output and the input. So basically that is the difference between this blue curve and the green curve. At 0, you see that the green curve is 0. The blue curve jumps up to 1/4 or minus 1/4. So if I take the difference between these two, at 0, what do you see? There will be discontinuity, and what will be the height of the discontinuity? 1/4. So it will jump up and down by 1/4. Let us say you go positive. This is constant, this is increasing. you take blue minus green, what will happen to the difference? It will go down. So actually draw this slightly more. Yeah. So when you take the difference, this is going to go down, and at this point both of them are equal, so it will come to 0. Let me quickly write it. And at this point, what will happen? There will again be a discontinuity. So let us say it will jump up like this, and then do this. So same thing will happen on the other side also. So something like this. So now you see the quantization noise is within plus or minus Vref by 4. And remember, ideally we wanted to use a gain of 2 power 2. So if I basically say, let me write it here, I am using a gain of 4. So the gain times the quantization noise is within the reference voltage. So we are fine. This is what happens normally. Okay. Now let's see what happens if there is an error, right? And for example, I'll consider that this reference voltage has an error. So let us say instead of comparing with 0, the ADC is comparing with this voltage. So again, I do the same thing. I take the difference between this curve and the green curve. So now where will you have the jump in the quantization noise? You will have it around this point. So which means this point will keep growing, and then at this point you will have the jump. So now it is clear that the moment you have any error in the comparator threshold voltages, the quantization noise in fact goes beyond Vref by 4. So which means if I use a gain of 4, the gain times quantization noise will exceed Vref. And this is a big red flag, because the entire business of cancelling the quantization noise relies upon the fact that the second ADC here is able to faithfully digitize the signal here. So if it exceeds the range, it's completely screwed up. So this will be a big problem. So what do you think might be a solution to this? Yeah, I mean, of course, one solution is to say that, hey, I'll go and make an excellent ADC so that this is not going to change. But obviously that's not practical. So the solution is, as he suggested, instead of having a gain of 4, we can try to use a smaller gain. So that's the solution we do. That's what we do in practice. So we use a gain smaller than the maximum gain, and the maximum gain in this case is 2 power 2. So what might be the gain value you use? G has to be less than 4. Tell me some number. Okay, seems like 3. Again, this is completely fine, but one minor point with using a gain of G is the following. Remember, the final data you reconstruct as V1 plus V2 by 3, or this is equivalently I can say 3V1 plus V2. Either of them is fine. Right? Now, which means I'll have to either multiply or divide by 3, and this is a non-trivial operation. Right? Multiplication or division by what kind of numbers are easy? Powers of 2, because that basically is right shifting or left shifting. So that's why typically we try to keep the gain to be a power of 2. Right? So in that case, what might be again use? Yeah, you basically use they'll say G to be G max by 2. That is something we can do. Again, there is no other, there is no hard rule saying you shouldn't use it. So let's say use a gain of 2 now. So I'm using a gain equal to 2, and I'm reconstructing the output as V1 plus V2 by 2. Again, let me take some quick numbers. So let us say V1, as we assumed, it's a 2-bit data coming from a 2-bit ADC. Let's assume V2 is say 3 bits. Okay. So when I do this, at the output I will have the input plus what will happen to the quantization noise of the first stage, that will get cancelled. So what will remain? Q2 by 2. So what will be the effective resolution? What is the effective resolution? I mean, the Q2 corresponds to 3 bits of resolution. Q2 by 2 is 3 plus 1, that is 4 bits. So again, let's see how you will have to do this operation. So let me write V1. V1 is 2 bits, so let's say it's x1, x2. V2 is 3 bits. So again, remember, we'll have to align the MSBs because the MSB bits of each ADC contains the same information. So that's what you'll have to align. So if this is V2, how will V2 by 2 look like? It will be right shifted by 1 bit. So which means this is now 0, all zeros. We are going to add this now. So now if you see that the addition is no longer the trivial concatenation you could do, you have to go and do this addition. And if I do this addition, how many bits I can get at the output maximum? Yeah, totally how many bits I can get? 5 bits I can get at the max, right? So now you see that the final digital output at the max can be 5 bits, but the effective resolution is only 4 bits. So that's why in the beginning I told, just because an ADC outputs 10 digital outputs doesn't mean the effective resolution is 10 bits. It can easily be smaller than that. Again, this is very similar to the redundancy case we saw in SAR ADC, right? Because in a SAR also we saw, to correct for any errors you make in the first comparison, you do redundant comparisons. So an n-bit SAR can give more than n bits at the output, but the effective resolution is still n. So this is something similar, so we also call this redundancy. And in particular, we say that we have 1 bit of redundancy because, I mean, it's obvious. Okay? Fine. So this how.
If we have given our first ADC of 2 bit, so our G will be 2 to the power 2.
That is the maximum gain you can use. Fine.
Like we don't have to need any extra circuit to convert it from 4 to 2. We can use maximum, we can use 4.
No, I mean this gain you are going to implement it. Where is the circuit? You will have to have some circuit to realize this gain. Instead of having a maximum gain, you use a smaller gain. So okay, so now let's play a game. So let's say I give you a pipeline ADC like this. Let us say 2 bit. For a 2 bit, what is the gain I will use with 1 bit redundancy? You will use 2 power 2 minus 1, which is fine. So let us say next is 3 bit. So once again I want to have a redundancy of 1 bit. What will be the gain I use? 2 power 2, which is 4. So let's say 6 bits if I use, what will be the gain I have? 2 power 5. And let's say at the end I have 4 bits. This is the final pipeline ADC you have, let us say. So what will be the effective resolution here? You have, how will you find it? Yeah, I mean, if I do this, the quantization noise of which ADC will remain finally? The last ADC will remain, and that will be divided by all these gains. So effective resolution is basically 4, 5. So how much you have? 9, whatever, 11, 12 bits. And in each stage you have 1 bit of redundancy. So totally you have, I mean, the effective resolution you have is how much? 9, 11, 12 bits. But the total number of bits you can have in the final digital data is basically 2 plus 3, 5, 11, 15. So you have 3 bits of redundancy, 1 in each stage. Okay. Cool. So now you know that if you make an error in the comparator threshold of your first ADC, by using a smaller gain, we can correct for it. So now you know if I make an error here, it is fine. So what is the next logical thing to ponder about? Huh? How much of an error you can make so that you can make a better design, right? You don't have to over design things. So let's quickly see how much you can have. So I'll take the ideal plot. I'm using a gain of 2. Okay. So which means I need to make sure that the gain times the quantization noise is less than Vref. So which means the quantization noise should be Vref by 2, less than this. So in each of the comparator reference voltages, I can make some error till the quantization noise is within Vref by 2. Fine. Again, we can easily find out how much you can make. Again, I'll take this as an example and do it, but the same will work well for either of the 2 references. So let's say I erase this now. So let us say now this level has an error. So which means this is going to go like this. Now I need to make sure this minus the input is less than 1/2, right? So remember at this point the quantized output is still 1/4. What should this be so that the difference is 1/2? Minus 1/4, and you see minus 1/4 is here, right? So which means I can make an error till this point. Sorry. Similarly, on the other side also you can do the same. Now let's quickly verify if the quantization noise is within the limits. So I'll erase this now. So now the quantization noise will show a jump at this point. So at this point you see this is 1/4, this is minus 1/4, the difference is 1/2. So basically it will grow, basically rise. So what is the maximum tolerable error I can have in each side? 1/4, that's basically Vref by 4, right? In one side is Vref by 4, other side also is Vref by 4, it is plus or minus Vref by 4. So same will hold good for basically each of the reference voltage. Is clear? This is pretty trivial to actually work out, and in general also you can find for an n-bit ADC, if you use let us say 1-bit redundancy like this, how much will be the tolerable error. So now let's restate what we observed. I know that, maybe I'll take the ideal quantization, this characteristic. So now I know that this level, even if it goes to the left by 1/4, I am fine. Similarly, this level, even if it comes to the right by 1/4, I am fine. Same I can say on the other side also. So this guy, if it comes to the right by 1/4, I am fine. This level, if it comes left to the 1/4, it is fine. So that's what made some people realize, I know that this can come here and this can come here. So instead of having 2 separate reference levels, why can't I actually merge them like this? Same thing here also, instead of having these 2 levels, I can simply merge the 2, right? If I do that, what will happen is this. Okay, I'll have to erase it. So I'll draw this. So now instead of having these 2, I'll have 1 at 1/4. Okay. So I'll be having 1 at 1/4. Hopefully this is slightly to scale. And similarly, these 2 will be merged. And I'll say I just have one more reference at plus 1/4. So we can have a quantizer characteristic like this. Now if you do this, earlier you need to compare with 3 reference voltages. So in a flash, how many comparators will you need? Huh? Yes. Okay, the idea is, I know that in each reference voltage, I can make an error of plus or minus 1/4. So the thought process was, this can go to the right by 1/4, I'm fine. This can also go to the left by 1/4, I'm fine. So it's merged. Same thing happens on the other side.
What do you mean by merging that?
I mean, let's say you make an error. I know that I can make an error till 1/4. Let us say you go and make an error. So this is now shifted to the right by 1/4. Similarly, this is also shifted to the left by 1/4, which means the two are same, right? This is basically merged like this. Huh? This is, sorry, V1, I'm really sorry. Yeah, okay, you are right. Thanks. 1 by 2. I mean, it can work out the range. We want to keep it symmetric. So you have to do this. Basically, if you want to keep it symmetric like this, again, see, what I was getting at is, the reason, motivation to do this is the following. If I were to compare with 3 reference voltages, how many comparators I'll need in a flash ADC? No, 3 reference voltages I need. Huh? No, 3 reference voltages are there. So you need to compare, you need 3 comparators. Fine. Now how many reference voltages I have? 2. How many comparators I need? 2. So it looks like the number of comparators has reduced. So that is one of the motivation. And again, the thought process is the following, right? I know that in a pipeline ADC, the final resolution only depends on the last stage ADC and the gains you have. I don't really care how many comparators I go and use in these ADCs, right? So this ADC resolution eventually sets a limit on the maximum gain, and you are obviously not using the maximum gain. So the idea is, I know that if I use a gain of, let us say, gain of maximum gain by 2, I can make some error in the comparator threshold voltages. So what we'll do is, we go and use the minimum number of comparators in each flash ADC, so that even if there is an error, gain times the quantization noise is within the range. Okay. The observation is this: I know this number of comparators here actually plays no role. You just have to make sure, even if you make an error, gain times the quantization noise should be within the range. That's all. For that, you use the minimum number of comparators required, and that gives rise to this. And we can actually check if the quantization noise will be within the range if you make an error. So let me maybe draw that again. So here, if I draw the quantization noise, let us say here I am drawing the quantization noise. Right. So I am taking the difference between the yellow curve and the green curve. So I take the difference between this and this. So initially it will do this, fine, and at this point it is going to jump, and remember that this value is 1/4, fine. So what will be the jump? I mean, it's 1/4 and 1/2, difference is 1/4. Here 0 minus 1/4, 1/4. So it's going to go up or down by 1/4 only. Again, it will do the same thing will happen here also. I'm just drawing it roughly. So once again, here you can find that even if one of the reference voltages, say this goes here to the right, you can work out what happens to the quantization noise. It will actually just grow as much as -1. That's all. So in this case also, even if you make an error of plus or minus Vref by 4, gain times the quantization noise will be within the reference voltage. Basically, I am redoing the same thing. Whatever we saw earlier, I am doing the ulta here. If it's not convincing, let's do that again. So let us say I make an error, this, right? So what will be the height of the jump? Here the green curve is 0, the quantized curve is, jump will be, that's all, yeah, negative half, that's all. So this is what we do, and here how many levels I have at the output? 3 levels. So remember, if I have 4 quantized levels, how many bits of resolution you say it to be? 2 bits. 8 levels. Similarly, if I have 3 levels, how will you find how much? What is the number of bits? Huh? No, I mean, can it be slightly more mathematical? 8 is 3, 4 is 2. So any number is log to the base 2 of 3. And this you work out, this is about 1.5 bits. So typically we call this the 1.5 bit stage. The motivation is this: you go and use the minimum number of comparators, so that even if you make an error, the quantization noise multiplied by the gain will be within the range for the next ADC. That's all. And this is particularly very useful in a flash ADC, because in a flash ADC, if you reduce the number of reference voltages you need, the number of comparators reduces. In a pipeline ADC, if you have, let us say, 10 flash ADCs used, the reduction will be significant. And in general, you can have, just like 1.5 bit, you can also have a 2.5 bit stage. So again, the thought process is very similar. Let us say you start with the 3-bit ADC. With the 1-bit redundancy, what will be the gain you use? Two power? Yeah, 2 power 3 minus 1, which is 2 power 2. So for this gain, you find out what can be the tolerable error in a 3-bit ADC. You can work it out. That will, in general, it's plus or minus delta by 2. Okay. So then what you do, you go and find out what is the minimum number of comparators I can have here, so that even if I make this error, this gain times quantization noise is within the range, and that will give you this 2.5 bit stage. So same thing you can generalize for an M+0.5 bit stage. So this was particularly popular when pipelining was done with flash ADCs, because reducing number of comparators meant a lot of savings in a flash ADC. This is the same thing. Let's say you have 0 and VDD. So you do the same thing, right? So here you know the reference voltages. It's minus Vref by 4 and plus Vref by 4. That's all. Oh, I mean, you start with the, as usual, right? You start with the 2-bit, and then you see, you know that you can make an error of Vref by 4. So each reference voltage, let us say you have 2 of them. Here it is basically minus 1/2 and 0. So here you go to the right, here you go to the left, and come in between. Similarly, you can do for higher bit resolution also. So this is how we kind of tackle any issues in the ADC. So where is the, yeah. So now we know if you make an error in the ADC, how you can tackle it. The solution is to go and use a smaller gain here, so that even if you make an error, you are fine.